Last time, we talked about the analysis of the runtime as a game. And basically, we had a matrix. I'm going to call that matrix C. And we assume that there are two players. We said that one player chooses the input to the input instance to the problem, and the other player chooses the algorithm. And we were assuming that we have a finite number of deterministic algorithms that we can choose from. And we also assumed that we have a finite number of inputs. So one player could choose an algorithm. Let's say the available algorithms are A1, A2 through AM. And the other player could choose the inputs. So input 1, input 2, all the way. Yeah, we have algorithms on one side, inputs on the other side. And so the two players, the one who's choosing the algorithms wants to minimize the cost. And the one who's choosing the input wants to maximize the cost. Right? And then instead of writing Cij, I usually just write C of AI and Ij, which means the cost of algorithm AI over input Ij. So we saw that if we let the algorithm player choose first, then that player can choose the algorithm that minimizes the cost, right? But what is the cost? Well, the next player, the one who's choosing the input, knows which algorithm has been chosen. So they choose the worst possible input for our particular algorithm here. And then the cost that we will get is the cost of running this algorithm on that input. So this is basically a worst case analysis, right? So if you fix any particular algorithm, this part, the max part, is just telling you what is the worst case runtime or worst case cost of that algorithm over all possible inputs. Okay. So this is what happens if we choose the algorithm first and then an adversary chooses the input. But the opposite case is that the adversary chooses the input first. So we first have maximum over all possible inputs. And then only afterwards, after knowing which input was chosen, we choose the algorithm. And then we will have minimum over all the algorithms. And then again, our cost is the cost of running this algorithm over this input. Okay. And we saw that for general games, these two are not necessarily the same. Right? Because we had this example of rock, paper, scissors, and we saw that they are not necessarily equal. But then we also saw that if we allow randomization, then they would be equal. Okay? So let's say that the first player, the player who wants to choose an algorithm, doesn't just choose an algorithm, they actually choose a distribution over all algorithms. And we said that a distribution over deterministic algorithms is basically a randomized algorithm. To be more specific, it's a Las Vegas randomized algorithm. But okay, so first, this player chooses a distribution, and then the other player can also choose a distribution. So let's call this distribution over algorithms, and this one distribution over inputs. And then instead of having just the cost, now we have the expected value of the cost. So this is the expectation of cost of running AI over input Ij. Okay, but what is this? What is the distribution that is defining this expectation? Well, our AI is sampled according to the distribution that the first player chose, and our input is sampled according to the distribution that the second player chose. Okay, and last time we saw that this is equal. So if we can have randomized solutions here, if instead of just choosing one strategy, you can choose a distribution over the strategies, we saw that it doesn't matter which one of the players chooses first. So this is equal to having the max player, the player who chooses the inputs, choose first. So that's max. Now, what does this player choose? A distribution over the inputs. And then the next player tries to minimize, but by choosing a distribution over the algorithms. And then again, we have the same expectation. So the expected value of the cost of running algorithm I over input J, assuming that the algorithm was sampled from this distribution and the input was sampled from this distribution. So, okay. So now the next step is to again look at this as a matrix game. Let's say that I am the player who chooses the algorithms. I'm the player who's choosing the rows of this matrix. I'm choosing which row to play. So if I fix some distribution, if I say that I'm going to choose my algorithm or my strategy according to this particular distribution, then assume that you are the other player who wants to choose an input. Well, you can just see what is the expected cost of the first input with my distribution of algorithms, what is the expected cost of the second input, and so on. And then you can just choose the single input that has the highest expected cost, right? So what I'm saying here is that after the first player has chosen this delta A, the distribution over algorithms, the second player doesn't need to choose a distribution over inputs. They can just choose a single input, the worst possible input. So instead of all of this, I can just write the same thing. But here, instead of just taking a distribution over inputs, this player just takes the worst possible input, so maximum over all inputs. And then the rest is the same. So the expected value of the cost of running this algorithm over this input. But now, the input is fixed, and we only have a distribution over the algorithm. So here, it's only the algorithm that is being iterated over. Okay. Now I can say the exact same thing on the other side. So on this side, I can say that if you fix a distribution on the inputs, if you tell me that the inputs are going to come from this particular distribution, then I can just look at the expected runtime of each one of my deterministic algorithms, and I can just take the best algorithm, the algorithm that has the smallest runtime. So again, if you choose a distribution here, you don't need to choose another distribution here. You can just choose a single algorithm. So this would be the maximum over all distributions on inputs as before. But now when I'm doing the minimum, I just take one algorithm AI that minimizes the expected cost. And then I will just have the expected cost of running my single algorithm AI on an input that comes from this distribution. Okay. Now, the last step that I want to do is this. I want to say, consider two distributions, one distribution over the inputs and one distribution over the algorithms, and just consider them arbitrarily. So I'm going to say I'm just going to add a star. So let delta A star and delta I star be arbitrary distributions. And this one is over the algorithms. And the next one, this one is over inputs. Okay. Now, I want you to just look at this part. So here, the algorithm player was choosing the best possible distribution, right? So now I want you to think, what happens if instead of choosing the best possible distribution, the player just chooses this distribution that we fixed here? Okay. So it used to be the minimum overall, but now we are just using a fixed one. So the value is going to increase. Okay. So what is the value that we have if the algorithm's player decides that this is my distribution? Well, it would just be the maximum over all possible inputs of the expected value of the cost of running AI with input ij, assuming that this AI is now distributed according to this distribution, the delta A star. But then that would be larger than this. Okay? So this is going to be greater than or equal than if we just took the minimum possible distribution. So minimum A, maximum ij, the expected value of C of AI ij, where AI is now distributed according to delta A. Sorry, yeah, according to delta A, not delta star. Okay, now I can do the same thing with the other side of this inequality. I can say that this side was the case where the player who was choosing the input was choosing the worst possible distribution, the distribution that really maximizes the expected cost. So now if he chooses any other distribution, this cost is going to go down. So in other words, if I just take the second part, minimum over all algorithms AI of the expected runtime and of the expected cost of running AI over ij, where I take my input not from the optimal distribution, but from this distribution that I fixed here. So from delta star I. Okay, this is going to be less than or equal to this. Okay, I'm going to write it again. So that's maximum over all distributions of inputs, then minimum over algorithms, and then the expected cost of running the algorithm over the inputs. And here, the only difference is that the input is according to this maximum distribution here. Okay, so, but here we had an equality, right? So I know that this is equal to this. Or in other words, this one is equal to this one. So this one has to be larger than or equal to this. So if I just write that, I will have that. Okay, let me say that this one is less than or equal to this one. So I want it in this order. Let's say minimum over all AI, the expected value of C of AI ij, where this ij is distributed according to delta star, is less than or equal to maximum of the expected value, and this is overall ij of the cost of AI and ij, if AI is distributed according to delta star. Okay, so after all of this, now what are these two sides? Let's just try to say what this inequality that we just proved means in normal speak in English. So here, what I'm doing is that I'm saying, suppose that I have given you a fixed distribution over the inputs and just find the best possible deterministic algorithm for that distribution and see what is the runtime. Okay, so this side is the expected runtime of the best possible deterministic algorithm assuming that the input is according to this distribution, assuming the input comes from that distribution that we have there. Okay. Now, what is this side? This side is saying that you can have a distribution over the deterministic algorithms. And a distribution over the deterministic algorithms is basically a randomized algorithm. Right? So all of this part is saying the expected runtime of a randomized algorithm. But that's the expected runtime, and then we are taking the maximum of the expected runtime over all possible inputs. So this is the worst case expected runtime of any. So worst case expected runtime of any randomized algorithm. To be more specific, this should be a randomized algorithm that solves the problem without errors. So it's a Las Vegas randomized algorithm. Okay. Now, what does this mean? This means that if you want to prove that for a particular problem, you cannot have, for example, a randomized algorithm that works in time better than n squared. What you can do is that instead you can just find a distribution over the inputs, and you can say that there is no deterministic algorithm that has a better runtime over this distribution. Okay? Now, what is the main difference? The main difference is that here, when I'm talking about expectation, the expectation is based on the randomness from the algorithm. Here, my algorithm is a deterministic algorithm. It's actually the best possible deterministic algorithm. And the expectation and the randomness basically comes from the input. So I have a distribution over the inputs. So on this side, I'm doing average case runtime analysis. On this side, I'm doing worst case expected runtime analysis of a randomized algorithm. So these two are now connected together. Okay. So how can we use this? So we can use it in the example that we saw in the last session. We talked about this min-max tree or and/or tree in the last session, which is, we said that TK is a binary tree that has K and levels and K or levels. So on. And I'm also assuming that the root is an AND level, but it doesn't really matter. You can also work with the opposite case. Okay, so we said TK is a tree like this, and then we have some leaves, and in each of the leaves, the input is given to us. So in each of the leaves, we will have a bit, either 0 or 1. And it's costly to read the input. So I want to evaluate the value of the root while reading as few bits as possible from the input. And we saw that no deterministic algorithm can do this without, in the worst case, having to read all of the leaves. So we have 4 to the power of k leaves. And we saw that the worst case runtime of any deterministic algorithm is at least 4 to the power of k. Then we saw, and by the way, we call this also n. So because n is the size of our input, so n is 4 to the power of k. Then we saw a randomized algorithm that can actually beat this runtime and solve the problem in 3 to the power of k. It costs 3 to the power of k. So that would be basically a randomized algorithm that has a runtime of O(n) to the power of the log of 3 in base 4. Whereas for deterministic algorithms, we couldn't do better than theta n. Okay? Or I only care about the omega part, so I don't care about the O part. Okay. Now, the question is, can we also find the bound on how good our algorithm can become if our algorithm is randomized? Can we find the lower bound and then say that even if you have randomization, you cannot be faster than this bound? That's what I want to do. Okay, so let's try to apply this rule. And what this says is that you can just pick any distribution for the inputs and then find the best algorithm, the best deterministic algorithm for that distribution. And the runtime of that deterministic algorithm on that distribution is going to give you the lower bound on the runtime of the randomized algorithms. Okay. Now, we talked about deterministic algorithms for this problem. And we basically talked about the fact that there are finitely many of them for any fixed k. There are finitely many deterministic algorithms that we actually cared about, right? And the idea was that the deterministic algorithm has to try to find the value of the children of a node before going to that node. But it can also do short circuiting. So if this is an OR node and one of its children evaluates to 1, then our deterministic algorithm does not need to evaluate the other child. So in the last session, we saw that, of course, you can have many other algorithms, but we saw that only these deterministic algorithms matter, right? So we saw that these are the optimal ones. So let's try to use that. But before doing that, I want to simplify my tree a little bit. And the way that I want to simplify it is by making sure that all the operations are the same. So now we have two different operations. We have AND and OR, but I want to have just one operation. And here's what I claim. I claim that I can replace all the operations in my tree with a NOR operation. So NOR is the opposite of OR. So if you write X nor Y, or you can read this as neither X nor Y, the negation of X or Y. Okay, so what does this mean? This means that X nor Y is 1 if and only if both X and Y are 0. Because even if at least one of them is 1, then the OR would be 1. But the NOR is the negation of the OR. So X nor 1 is 1 only if both X and Y are 0. Okay? So now what happens if I replace my tree, replace every operation in my tree with a NOR? Basically, I'm going to say that the value of the root is not going to change, but I can just do it level by level. So let's just take a simple tree like this. So let's say I have an AND here, and then I have OR here, I have OR here. And then let's say I have the leaves. So let's say this is leaf number 1, leaf number 2, leaf number 3, and leaf number 4. And each of these are 1 bit. Okay. So what I'm doing is that I'm taking this tree and I'm changing all the operations to NOR. So I have NOR, 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 and then here I have L1, L2, L3, L4. And what I claim is that the value of the root does not change. Okay, so what is the value of the root here? It's L1 or L2 and L3 or L4. Okay, so I want to write this formula only using NOR. Okay, so if I have L1 or L2, well, if I want to change this OR to a NOR, I can just take a negation. So this is the negation of L1 NOR L2 and the negation of L3 NOR L4. Okay. So what can I say about this? Let's just go here and prove something else. So if I have not P and not Q, how can I write this using NOR? I can say that this is just P NOR Q. Right? Because not P and not Q says that both of them, both P and Q, have to be 0. And that's the same as saying P NOR Q. Okay, so I can write this one. Okay, so let's say that this is my P and this is my Q. So this is going to just be L1 NOR L2 NOR L3 NOR L4. And this is what this tree would give me. Okay. So I can replace all of my operations with NOR. And okay, in this tree, I can first do this from on the bottom 2 levels and then do it in the next 2 levels and so on. So I can change everything in my tree to a NOR. Now, this was assuming that the root of my tree is an AND node. If the root of the tree is an OR node, then you can replace all of the operation with NAND, which is the negation of AND. And it would be exactly the same idea as here. So I'm just going to assume that the root of the tree was AND, and so I'm replacing everything with NOR. Okay, so now I have a NOR tree, and its depth is 2k. It has 4 to the power of k leaves. And I'm thinking about giving it some distribution over the inputs so that even the best possible algorithm cannot really solve it fast. Okay. So let's say I have NOR everywhere. So all of these are NOR. Okay, so I fix some distribution. Let's call it just like there. Let's call it delta star of I over inputs. Okay, and by the way, the set of my possible inputs is also finite. Right? I don't care that it's really big, but it's finite because I have depth k. And so I have 4 to the k, I have depth 2k. So I have 4 to the k different leaves. And for each one of them, I can choose it to be 0 or 1. So the number of possible inputs is 2 to the power of 4 to the power of k. Right? But the important thing is that it's finite, because when we wanted to do our game theoretic analysis, we wanted to say that mathematically speaking, we can write it as some sort of matrix, and then this matrix would need to have finitely many rows and finitely many columns. So here we have finitely many inputs, and as we talked about before, we also have finitely many deterministic algorithms that we really care about. Okay, now how do I want to fix this input? Well, I want to make sure how do I want to fix this distribution over the inputs? I want to make sure that for any given node in this tree, the probability that the value of that node becomes 1 is the same as the same probability for any other node. Okay, so I want to do it in a way that for any internal node here, the probability, I have some probability P, and P is the probability that this node evaluates to 1, and I want it to be P for every node. Okay, so how can I do this? Well, let's just look at a simple example at what happens at some children. So let's say I have 2 leaves. Let's call it L and L prime. And they have the same parents, and we have a NOR here. Okay. So if each one of the leaves has a probability P of being 1, then what is the probability that the parent is also evaluating to 1? This one evaluates to 1 with probability P, and this one also evaluates to 1 with probability P. But this one evaluates to 1 only if both of these have evaluated to 0. So the probability that this one evaluates to 1 is 1 minus p squared. Okay? But I want this to be the same as p. So I just need to solve this equation. I just need to be sure that 1 minus p squared is equal to p. Okay, and this is a quadratic equation. You can solve it. And since this is a probability, we want it to be between 0 and 1. And if you solve it, you'll see that there is only one solution between 0 and 1. And that's 3 minus square root of 5 divided by 2. Okay? So that's how I fix my input. I say that I take every one of these bits, and with this probability, I set it to 1. Okay. Now, what is the best that an algorithm can do? So this one here, p is 3 minus square root of 5 divided by 2. We said that any deterministic algorithm, in order to find the value of some node, has to first find the value of its children, right? So let's say that I have some node here, and let's say that the height of this node is h. Okay? And let me call it, I don't know, let me call it C of h. So let's say C of h is the expected cost of finding the value of a node that is at height h. Okay? So this is norm, right? So what does the deterministic algorithm do? It goes to one of its children first, and we don't know which one because we don't know which deterministic algorithm we're using, right? But in any case, I just want to find the bound here. It goes to one of its children and evaluates that one. So that's going to take a cost of C of h minus 1. Now, if this child is a 1, then we already know that the answer here is 0. So we will not go to evaluate the other one in an optimal deterministic algorithm. But let's take the worst case. The worst case is that this child is 0. And if this child is 0, then we go and evaluate the other one. But we chose our inputs in a way that we can actually know what is the probability that this child gives us 0 and what is the probability that it gives us 1. So if this child is 1, well, I have to do this much work, but the probability that this child was 1 is just p, right? But if this child is 0, then that is probability 1 minus p. And how much work do I have to do? I have to basically evaluate both sides. So this would be times 2c of h minus 1. Okay. Let me see. Yeah, with probability p, we just go one side. With probability 1 minus p, we go to the other side. But I can just write it like this, right? So I can say my cost for height h is just my cost for height h minus 1 plus 1 minus p times the cost for height h minus 1. Okay, now this is a nice recurrence, and actually we know the value of p, so the value of p is that. So you just put the value of p here and find the cost for every node. And if you do that, what you get at the end of it, and I don't want to again do all the calculations, but this is a simple thing that you can solve. So what you will get at the end is that the cost for height 2k, which is the cost for evaluating our original tree, is greater than or equal to n to the power of 0.649. Okay, and that's because just that's the solution to this equality. It's like every time that you increase the height by 1, you're increasing your cost by a constant factor. So this is just increasing exponentially in terms of the height. So you just solve it for height 2k, and this is what you get. And this is, again, assuming that n is 4 to the power of k. Now, so what do we know? Now we know that for this particular distribution that we chose, there is no deterministic algorithm that can solve this problem in a time that is better than this. So now we can come back here. So the expected runtime of the best possible deterministic algorithm over an input distribution that we could choose, and we did choose, is a bound on the worst case expected runtime of any randomized algorithm. So this proves that I cannot have a randomized algorithm that has a runtime better than this, expected runtime better than this. So now what do I know about my randomized algorithms? Well, I have a randomized algorithm that has this runtime. What was this value? Let me see. 0.7925. Okay. So I have a randomized algorithm that has this runtime, and that's the algorithm that we saw last time. But I also know that I cannot have any randomized algorithm that has a runtime better than this. So now I have both a lower bound and an upper bound, and I know kind of how well I can do. Unfortunately, these two numbers are not the same, right? So I know that I can't do better than this, but the algorithm that I have is actually taking more time. Now, I'm not going to do a more involved analysis here, but this is actually optimal. So if you just choose your distribution in a way that is much smarter than this, then you can get a better bound here, and you can actually match this one. Okay? But anyway, this is how you find bounds on the expected runtime of the best possible randomized algorithm. Okay. Now I want to continue and go to another simple technique that we often use for analyzing randomized algorithms. So I'm just giving you more and more techniques. So one technique is this one, the game theoretic technique for finding a lower bound. But now I want to again go back to finding upper bounds. And I'm going to do this one with an example. We started this course by talking about quicksort, but there is also like a sister algorithm of quicksort, which is called QuickSelect. And I think that you've seen this in your undergraduate courses as well. This problem is that you're given an array, and this array has n elements. So the input is an array of n elements. And let's just assume that we can always compare these elements. So just assume that these elements are small integers. I can compare them. And I also give you some index k. And what I ask you is to give me the k smallest element in this array. Okay. So the output you should give me is the k smallest element. Now, if k is equal to 1, you just need to give me the minimum of the array. So you can definitely solve that in linear time. You can just go over the array. If k is a small number, you can also do the same. You can just go over the array and always keep track of the k smallest elements that you have seen until this point, right? And that would give you an algorithm with a runtime of O n times k. But the problem is when this number k is not so small. So if k is, for example, n divided by 2, if I want the median element, then these kinds of algorithms would actually give us quadratic time, which is off. Okay, so what does QuickSelect do? It does something very similar to QuickSort. It says I have an array, and this array has n elements. What I do is that I just choose some pivot element. So let's say I take this P, which is a pivot. And then I break the array into two parts. Or again, actually 3 parts. So I have my pivot element. I have all elements that are less than or equal to my pivot element. And I have all the elements that were larger than my pivot element. Okay. Now I'm looking for the k smallest element. So if I have k minus 1 elements here, then the k smallest element was just my pivot, and I was really lucky, and I just returned the pivot. Otherwise, if I have more than k minus 1 elements here, then I have to find the case element in this subarray, and I can just ignore that subarray, which was greater than p, right? Otherwise, let's say that I had t elements here, and let's say that t was less than k minus 1. So the case element is here. But what is the index of the case element here? Well, we have k elements that are smaller than everything here. Sorry, we have t plus 1 elements that are smaller than everything here. So I can just search in this array for the element with index k prime, which is k minus t minus 1. Okay, so I just have to change my index and then search it. Now, what I want to do is not to analyze the runtime of this algorithm. Actually, analyzing the runtime is quite easy, and it's very similar to what we saw for quicksort. What I want to do here is to analyze the depths of the recursion, right? So every time it's like I do a function call here, and then it recursively calls itself either on this side or on that side, and it just continues this. And I want to see how many recursive calls can I have? How deep can it go? Okay. So let's say that I say T is the depth of recursion. And of course, T will depend on N, which is the size of the array. And what I'm interested in is the expected value of T. And I want to show that this expected value is at most some amount. So I want to show that the number of times that I call my same procedure recursively is bounded. Okay. And I want to find the bound on it. So how do we do this? Well, there is a technique that we use very often, and it's actually a very simple lemma. And this is the technique. So make sure that I use the same notation as the book. Okay. So let's just call it a lemma. I want to say that I'm solving the problem over an instance of size n, okay? But the size of my instance gets shrinking over time. So I'm just going to use m to talk about the current size of my instance, okay? And the way I want to think about it is that I have a function g that goes from natural numbers to natural numbers, let's say, or maybe from z to z. And I want to say that if my instance size is m, then on average, in one step, I will go to an instance that has a size that is m minus g of m. Okay? So I just want to have some measure of how fast my instance size decreases. So g of m is the decrease if my instance is of size. Okay. But what I want to do is to be much more formal here. So after that, I'm just going to say, let G. And actually, I think it would be better if I define this over real variables. So let's say that G maps reals to reals, non-negative reals to non-negative reals. And let's say that this is a non-decreasing function. Okay. Now I want you to maybe think of this as some sort of insect that is jumping. So let's say I have a 1D world and I have an insect, and let's say that that insect is initially at position n. And let's say that, okay, this is 1. And let's say whenever the insect is at position m, it would just jump to position m minus x. But this x is randomized. Okay? So suppose that g is this non-decreasing function. We are originally at point n. In each step, we go from m to m minus x. And now this is the part where I want to use my function g. The only thing that I know about this is that the expected value of x is greater than or equal to g of m. Okay, so again, I'm starting here. Let's say I'm an insect, I'm at point n. I just keep jumping until I get to point 1. And every time when I want to jump back, I jump from m to m minus x. And what I know is that the expected value of x is more than some function. I don't know that function right now. You can think of this as the size of instances there. So I start with an instance of size n, and every time I jump to an instance of smaller size until I get to an instance of size 1 and my problem is solved. Okay. And actually, so I can also say that this x is always in the set 1, 2 to m minus 1, right? Because I'm always decreasing the size of my instance. Now, I want to define this t. T is the depth of recursion. So I say let t be a random variable, but it's be the number of steps until we reach 1. Okay. Now I want to find a bound on t. And the bound is this. The expected value of t is at most the integral from 1 to n of 1 over g of x dx. Okay. As you see, suddenly we went to a continuous world. And I'll prove it for you, and then I show how we can use it here. But before proving it, I just want you to understand the intuition here. So the intuition is that whenever I'm at some position, I'm going to the right here or to the left according to where I stand. So I'm decreasing my position by x units, and the expected amount of the decrease is g of m, right? But the decrease depends on where I am right now. So if I started at m and the decrease did not depend on m, then as I went to the left, I would jump by g of m steps each time. And then the number of jumps that I would need would be just n divided by g of m, right? But this step size is changing. And so since it's changing, I have to take this integral. That's the whole idea here. But let's prove this formally. Okay. What is the expected number of steps that I will take? So I'm assuming that I'm starting at position n. So I first take one step, right? And when I take one step, I will be at position, let's say, n minus x. So this would be 1 plus the expected value of my cost or my number of steps from n minus x. Okay, so let's say that I know that the inequality holds for every smaller value of n, right? So when I'm talking about the number of steps from n minus x, I know that the number of steps from n minus x is at most this much, where I have to put n minus x instead of n. Actually, let me give that a name. So I'm just going to call this one f of n. Okay. So f of n is this integral. So my expected number of steps is at most 1 plus the expected value of f of n minus x. And that's it. And the only thing that I know is that the expected value of x is greater than g of n, because I'm starting at position n right now. Okay, so let's expand this. This is 1 plus the expected value, and let's just use the definition. So f of n was this. If I want f of n minus x, that's the integral from 1 to n minus x of 1 over g of x dx, right? But if I have integral from 1 to n minus x, I can write it as the integral from 1 to n minus the integral from n minus x to n. Okay? Now, what is this one? This is f of n by definition. So I have 1 plus f of n minus the expected value of that integral from n minus x to n, 1 over g of x. Okay. Now what can I do? So now I want to use this assumption. I want to use the fact that my function g was non-decreasing. Okay. So I can say that this is at most, I keep all of these things, but here instead of g of x, I just put g of n, because my function g was non-decreasing and I'm finding a bound. So this would be 1 plus f of n minus the expected value. Well, now if it's just 1 over g of n, that's a constant. Right, so expected value from n minus x to n, 1 over g of n dx. Okay, but this is a constant. And I'm integrating a constant from n minus x to n. So I just get the length of the segment times this constant. So the integral, I'm going to continue here, is equal to 1 plus f of n minus 1 over g of n was the constant, and the size was just x. Right? But I'm also taking expectation, so I have to write it like this. Expectation of x. Okay? But here's the thing. I have this assumption for every m, including for m equal to n. So I know that this numerator here is larger than the denominator. So this whole thing is larger than 1. So this whole runtime is at most f of n, because I can cancel this one with this one. Okay. So that's the proof. But again, what I want you to really remember is this, that if on average we are decreasing by g of m, then the total number of steps would be the integral. Okay. So let's apply this now to QuickSelect. I'm erasing this one. So if I have a QuickSelect and I want to find my function g, what is my function g? So my question is, if I'm starting with an instance that has m elements, okay, what is the average decrease in the size that I will have? So I want to find a bound on x, on the expected value of x. Now, it all depends on my pivot, right? But I'm choosing my pivot totally randomly and uniformly at random. So every pivot is equally as likely as every other pivot. Now, if the pivot that I choose is greater than, is in a position that is larger than k, then I have to look behind the pivot. Otherwise, I have to look after the pivot. But I just want to find a bound. Okay? So if I want to find the bound, we can go back to the idea of some pivots were good for quicksort and some pivots were bad. So let's just take that and let's take k entirely out of our equation. So we just assume that whenever we take a pivot, we are really unlucky and we have to search on the larger side. Okay? So what is the probability that the larger side is at most, let's say, 3/4 of the original side? Okay. So if I want that, if I want the largest one here to be more than 3/4, then the element that I choose should either be in the first fourth or in the last fourth. So I have a half chance of decreasing this to at most 3/4 times n. And I have another half chance that my size is large. So I take the worst case and I say, let's say that's m-1, right? I'm just finding a bound so I can be sloppy with the bound. Okay, so, sorry, this was not the expected value of x, this was the expected value of m-x, right? Because x was supposed to be the amount that we reduce from our size. Okay, so what is this? This is 3/8 of m plus 4/8. 3 and 7 is 7/8 m. So this was m-x. So if I want to find the expected value of x, that's at least 1/8 times m. Okay, so x is the decrease in the size of our instance. And basically what we're saying is that if I start with some instance that has size m, on average, after I do one step of my algorithm, I expect to be left with an instance whose size has decreased by at least this much. So whose size is at most that much. Okay. This is not a good bound. You can probably prove 1/4 as well. Sorry. Oh, I'm just assuming that it was m. So I'm saying that this is 3/8 of m and this is 4/8 of m. So overall, it's no more than, okay, yeah, I have to say something like no more than 7/8 of m. Okay, yeah, it wasn't equal exactly. But anyway, what I really care about is this function. So this is my function g, which shows how much decrease I have in the size of my instance. And this is 1/8 times m. And you can also check that, of course, it's non-decreasing. So 1/8 of m gets larger as m gets larger. So I have all the conditions of there. And so I can say that the expected number of steps is at most the integral of this function. Okay, so this is the integral of from 1 to n of 1 over g of x. So 1 over 1/8 of n. X. Okay, so this is just the integral from 1 to n. I take this 8 out. It's 8 times this integral of 1 over x d of x. And we know that this integral is basically the natural logarithm, right? So this would be in O of log n. So basically what we proved is that if we do QuickSelect, on average, the number of iterations that we expect to have before we get to the trivial case where we have only one element is log n iterations. Okay. Now, of course, you can combine this with the fact that every iteration takes at most time at most n, and you can say that so our overall runtime is at most n log n, right? But actually, the overall runtime can be analyzed to be even O(n). So this kind of analysis doesn't really help you get a good bound on the overall runtime, but it definitely does help you in finding a great bound on the number of iterations that you have. Okay. We have a few minutes, and I just want to show you one other algorithm, if time permits. And I want to go back to our favorite problem, QuickSelect, and I want to look at one of its special cases, or one of its extensions, maybe. So this is the problem I want to look at. It's called Max3SAT. Okay. The input is just a 3-SAT instance. So the input is the same as 3-SAT. So we have, for example, a formula, and the formula is like x1 or x2 or not x4 and let's say x5 or x3 or so on and so on. And as I said previously, we say that each one of these is a clause. So every clause is the result of disjunction of 3 literals, but this is what I mean by a clause. Okay, so now the output, now in a normal 3-SAT instance, what you would be asked for is to find some valuation for all the variables so that all the clauses are satisfied, right? But now here I want to say find a valuation such that the maximum possible number of clauses are satisfied. Okay? Or if I want to do it without a valuation, I can ask what is the maximum number of clauses that can be satisfied using a single valuation. Then you can ask for the valuation, or you can ask for the number of clauses. It doesn't really matter. So basically the idea is that 3-SAT is hard. It's an NP-complete problem. So if you give me a 3-SAT instance, I might not be able to find a valuation for every clause, a valuation that makes every clause satisfied. But maybe I can find a valuation that satisfies a lot of the clauses. So now the question is, what is the maximum number of clauses that you can satisfy? Now, this problem is, of course, also NP hard, because this is harder than normal 3-SAT. But can we maybe approximate it? Can we use randomization here? So what happens if I just randomly give values to all of my variables. So for each variable x1, x2, up to xn, I just flip a coin, and with probability half, I assign true to that variable, and with probability half, I assign false. Okay? So how many clauses would I satisfy if I do this? Okay, so let's say that x is the number of satisfied clauses. And well, I can use indicator variables. I can say xi is 1 if clause I is satisfied, and it's 0 if clause I is not satisfied. So then I can just say that x is the sum of xi's. So I can use linearity of expectation. So x is the sum of the xi's, and so the expected value of x is also the sum of the expected value of xi's. Okay, but what is the expected value of an xi? Well, since this is an indicator variable, the expected value is just the probability that this particular clause holds. Right? Now, the probability that this clause holds, well, you can compute it easily. Let's say that no clause touches the same variable more than once, so I don't want to have x1 or x2 or x2 because that's weird. So if I have cases like this, I can say that in order for this clause to be satisfied, at least one of these three literals inside it should be satisfied. And each one of them have a probability of half to be satisfied. So the probability that none of them is satisfied is 1/8. And so the probability that this clause is satisfied is at least 7/8. Okay? So then this is just the sum over all clauses of more than the sum of 7/8, which is basically 7/8 times the number of clauses. Now this is great, right? So in the best case, all of the clauses are satisfied. But no matter what's happening, our algorithm on average satisfies 7/8 of the clauses. So this is a 7/8 approximation, right? And that's a relatively good approximation. It's a constant number. But we got it with randomization, so it's not guaranteed that if I run my randomized algorithm once, I will get a result that is this good. But again, maybe we can use the idea from previous sessions where we just ran the algorithm over and over again until we got a good approximation. So what happens if I run the randomized algorithm, let's say n times, and then after n times, I just take the valuation that satisfied the maximum number. You can then analyze it using the tools that we've seen before. But I want to use this to go into a topic that we will cover in more depth later, and that's the topic of de-randomization. So the idea of de-randomization is that you have some randomized algorithm, and you want to somehow use the ideas in that randomized algorithm to get a deterministic algorithm. So I have this simple randomized algorithm here. Let's say I want to find a deterministic algorithm that gives me a 7/8 approximation of the number of clauses. Okay? How can I do this? Well, I can say that just think about the randomized valuation that we were supposed to give, which was that we set every value, every x to 0 or 1 with the same probability. Don't use it in the algorithm as randomization, but use it to analyze what happens. So here's the thing. I take x1, And what I can do is that I can say x1 is either going to be true or false. If x1 is true, what is the probability that I set x1 to true? It's half, okay? But assuming x1 is true, what is the expected value of the number of clauses that will be satisfied? Well, I can go to every clause that has x1 and I can just mark that one and say this is definitely satisfied. Then I can go to every clause that has not x1 and I can remove not x1 from that clause because that's not going to help with the satisfaction. And then I can compute the expected number of clauses that will be satisfied if I use my randomized algorithm. Okay? Now I can do the same thing, but setting x1 to 0. So I just do both of these things. I first set x1 to 1, and I compute the expected number of clauses that will be satisfied. Then I set x1 to 0, and I compute the expected number of clauses that will be satisfied. And then I compare. And this tells me whether it's better for me to set x1 to 1 or 0. And if the expected number of satisfied clauses was larger when x1 was set to 1, then I just set x1 to 1, and then I move to x2 and do the same thing again. Okay? So this is what I'm doing. I'm saying for every xi in my set, so from x1 onwards, first set x1, set xi to true, and recursively, or well, not recursively, but it's just going over it, and find the expected value of x, assuming that xi is true. Okay? Or actually, yeah. And then do the same thing. So find the expected value of x, assuming that xi is false. And just continue based on that. I want to write a nice pseudocode here so that I just do something like this. I can have some v that basically gives me values for the xi's, and originally v is empty. And then I just say for every I from 1 to n, here's what I want to do. I want to compute two things. I want to compute the expected value of the number of clauses that are satisfied, assuming that x1 is v1, x2 is v2, so on, and xi minus 1 has value vi minus 1. But at the end of it, I want to set the value of xi to true. Okay? So this is the first value that I compute. Let's call it t. And then I compute f, which is the same expected value. So I keep all the values that I had for the previous variables, and I set xi to false. Okay? And then I say if t is greater than f, then just set vi to be true. Vi is true. Otherwise, vi is false. Okay, so my algorithm is just going over every possible xi and checking its value. So we already have fixed the value for all the previous variables. For this variable, we check what happens if we set its value to true, what happens if we set its value to false. And get this expected value based on that result. Okay? Now, the nice thing is that this de-randomized algorithm is not really using my randomized algorithm, it's just analyzing my randomized algorithm. There is no randomization here. This is a deterministic algorithm. Right? It's just using the computation of this expected value to decide where to go. And you can easily prove that now this deterministic algorithm also gives us a 7x algorithm.